This video will describe the theoretical basis of the Huckel rule. We'll look at examples of heterocyclic and ionic aromatic rings and discuss how you can discriminate between ortho, meta, and para disubstituted benzenes using NMR spectroscopy. You've already seen the four criteria required for molecules to fit into the categories of anti-aromatic and aromatic compounds. The main difference between the two being the number of pi electrons in the conjugated system. The basis for Huckel's rule is best explained using MO theory, which permits a better explanation of bonding in aromatic systems. It describes bonds as mathematical combinations of atomic orbitals that form a new set of orbitals called molecular orbitals, where if you have n atomic orbitals, they combine to form n molecular orbitals, and that's shown in this example where we have two p atomic orbitals mathematically combining, and this is how we can show it on paper. We're not going to go into the mathematics, but we'll use these little diagrams. They combine and they form a pi bonding molecular orbital, and they also form a higher energy antibonding molecular orbital. So two atomic orbitals form two molecular orbitals, one bonding, one antibonding. Taking benzene as an example, if we mathematically combine the 6 p atomic orbitals, one residing on each carbon of the benzene ring, we end up with 6 molecular orbitals, 3 of which are bonding, all lower in energy than the original 6 atomic orbitals, and the other 3 are antibonding, all higher in energy than the original p atomic orbitals. If we take the 6 electrons that were one in each of these p atomic orbitals, we have to place them now in the molecular orbitals. And the rules for filling molecular orbitals is the same as the rules for filling energy levels of atomic orbitals. We start at lower energy and work our way up. And you get an arrangement that looks like this. So molecular orbital theory says that a compound is particularly stable if all of its bonding molecular orbitals are filled with para electrons. So that's true of all aromatic compounds. And benzene, as you can see here, the 6 pi electrons are distributed in the 6 molecular orbitals, none of which are in the antibonding, all of which are in the bonding molecular orbitals. And you'll notice that benzene's molecular orbitals that are bonding are all completely filled. So one way of rationalizing the extra stability of benzene is to compare it to the extra stability of the noble gases, in which they had their outer valence shells filled with electrons. So in much the same way, benzene and other aromatic compounds will have their bonding molecular orbitals all filled with electrons, and it gives them this extra stability. Molecular orbitals can be placed at points where the vertices of a hexagon contact a circle in which it is inscribed, and you'll notice that with the 6-membered ring of benzene, if you draw it in such a way that it has a vertex, one of the vertices is pointing down, it hits the edges of the circle right at the positions of the energy levels of the molecular orbitals that you would get from the mathematical calculations. So you don't have to actually work out the mathematics in order to come up with an energy level diagram like this, a molecular orbital energy diagram. All you need to do is take the ring size that you're working with, inscribe it in a circle, draw it so that one of the vertices is pointing down, and wherever the edge of the ring, one of the vertices, touches the circle in which it is inscribed, that's going to be where the energy level of one of the molecular orbitals. And if you draw a line right through the middle of the circle, above that line would be antibonding, below that line would be bonding, and on the line itself would be non-bonding molecular orbitals. What I just described on the previous slide can be demonstrated by looking at the 6 examples here. Notice that each of the rings are drawn with a vertex pointing down. And if we draw a circle around each of the rings, then draw horizontal lines through each carbon on the ring, you'll see that marks off where each of the vertices touches the circle, and at that point, those positions represent the relative energies of the molecular orbitals that you would get from a mathematical calculation. If you draw a horizontal line through the center of each circle and label the molecular orbitals, you would say that those which are above the line are antibonding. Those which are on the line, like these, would be non-bonding. And those which are below the line would be bonding molecular orbitals. If we place electrons in the molecular orbitals, you see that those which have 4n plus 2 pi electrons accommodate all of their electrons in the low energy bonding molecular orbitals, and they're aromatic. So notice that in this case here, bonding molecular orbitals are full. In this case here, the bonding molecular orbitals are full. The same for benzene, and the same for this cation. So they meet all the criteria for being aromatic: cyclic, conjugated, planar, and 4n plus 2 pi electrons. In contrast, those which have 4n pi electrons have 2 electrons in separate, degenerate, meaning of equal energy, molecular orbitals, and they act like biradicals. So when you have an unpaired electron, it's a radical. And you've learned that a radical is a reactive mechanistic intermediate, and they are very reactive. So that's making these anti-aromatic compounds unstable. Therefore, anti-aromatic compounds, because of their biradical nature, are particularly high energy, reactive, unstable. And molecules like cyclooctatetraene, which are cyclic, conjugated, and have 4n electrons, they will choose to adopt a non-planar shape, non-planar conformation, rather than a planar conformation, because the planar conformation would give them all 4 characteristics that are required to make it anti-aromatic. So cyclooctatetraene, rather than being planar, is non-planar, and the molecule is simply just a typical alkene, a molecule, a ring that has 4 typical alkene double bonds in it, and those double bonds would react in the same way that any alkene would by a typical electrophilic addition reactions like the one shown here. We can refer to benzene as a carbocycle, that is a ring whose members are entirely made up of carbon. When you have a ring that contains, in addition to carbon, at least one other atom besides carbon, for example, oxygen, nitrogen, or sulfur, they're referred to as heterocycles, and these atoms would be referred to as heteroatoms, that is, atoms other than carbon. Heterocyclic compounds can be aromatic, and when you are trying to determine whether or not a compound is aromatic, you have to always consider the Huckel rule by looking at the number of electrons in the conjugated pi system. So for heteroatoms that have non-bonded electrons attached to them, you have to determine whether or not you include them in the count of the electrons for the Huckel rule. So is the heterocycle pyridine aromatic? What about these electrons that are attached to the nitrogen? Do I add them into the count of the 2, 4, 6 electrons that are in this ring? And do I make that 2, 4, 6, 8? Well, you have to consider the hybridization of the heteroatom. In the case of pyridine, yes, it is aromatic. These 2 electrons that are attached to nitrogen are in an sp2 hybrid orbital. This nitrogen is sp2 hybridized, and its p orbital here with the 1 electron, that 1 electron is part of this cyclic array of electrons that are making up the aromatic ring. And these 2 electrons, these non-bonded electrons on nitrogen, are in an sp2 hybrid orbital, which is perpendicular to these p orbitals, so there's no way that it can get involved in conjugation with these electrons. So we do not count those when we're adding up electrons to make up the Huckel number of electrons. Compare pyridine with another heterocycle called pyrrole. This also has nitrogen as part of the ring, and it has non-bonded electrons. And you might be wondering whether it's, is this sp2 hybridized nitrogen? Is it sp3 hybridized nitrogen? Well, pyrrole, if it was planar, would meet the criteria of being aromatic because it is cyclic. If it was planar, these would be conjugated, and you have 4n plus 2 pi electrons. So is pyrrole aromatic? It is. Nitrogen will be sp2 hybridized so that these 2 electrons can get involved in conjugation, giving you a Huckel number of electrons, and therefore pyrrole is aromatic. So remember that aromatic compounds are particularly stable compounds, and that's a driving force. If a compound can be aromatic, it will be aromatic, or if it can become aromatic, it will become aromatic. Ions can also be ionic compounds, that is, negatively and positively charged compounds, can be aromatic if they do meet the criteria for aromaticity, those 4 criteria. In the case of the cyclopentadienyl anion, it does. It is cyclic, it is conjugated, it is planar, and it has 4n plus 2 pi electrons. This carbon is sp2 hybridized so that these 2 electrons can get involved in the conjugation. How do I know that this is a completely conjugated system? Well, one way to do that would be draw all the resonance structures for the cyclopentadienyl anion, and that's shown below. And you'll see that I start with this resonance structure, and by pushing electrons around, you can see that the minus charge eventually will end up on every single carbon of the 5-membered ring. As you know, having the correct number of pi electrons, 4n plus 2, the Huckel number of electrons, is vital for a compound to be aromatic. And although the cyclopentadienyl cation and radical also have resonance structures in which the positive charge or the radical can sit on every carbon of the 5-membered ring, it's only the cyclopentadienyl anion which is aromatic because of the fact that it contains 4n plus 2 pi electrons. So all of these systems are planar, they're cyclic, they're conjugated, but only this one, the anion, has the right number of electrons, making this the only species of the 3 to be aromatic. I mentioned a few moments ago that if a compound could become aromatic, it would. because of the extra stability of aromatic systems. That would be a driving force for chemical transformation. And that's exemplified here with cyclopentadiene. Here you have a compound which is non-aromatic, and when you compare the pKa of this particular hydrogen versus, say, the pKa of a typical hydrocarbon hydrogen like cyclopentane, very non-acidic. You rarely ever see, or you won't see, any simple hydrocarbon losing a proton to become an anion. These are very non-acidic, very high pKa. But look at the pKa of cyclopentadiene. It's very low. It's almost like water, right? pKa of close to 16 for water. Why is it this hydrogen is so easily removed? Why is it that this bond is so weak? And the reason is because when you break this bond, these two electrons will reside on this carbon. It goes from being sp3 hybridized to sp2 hybridized, and these two electrons here can enter into the conjugated system, making an aromatic cyclopentadienyl anion. So that's a driving force for breaking this CH bond. A classic example of an aromatic cation is the tropylium cation. And you can see that this molecule is cyclic, it's planar, it is completely conjugated, and it has 4n plus 2 pi electrons. All of the carbon atoms are sp2 hybridized. Therefore, all of the p orbitals are parallel to each other, and this system is completely conjugated, and you can tell it's completely conjugated by drawing all the resonance structures for the tropylium cation, and you will see that you will get a series of resonance structures in which the positive charge is distributed on each carbon throughout the ring. Try this yourself, and this was actually one of the problems in the resonance structure problem set, solutions of which are posted on Blackboard. One final topic, and that involves NMR spectroscopy of disubstituted benzenes. How can you distinguish between ortho, meta, and para disubstituted benzenes? We'll start with symmetrically disubstituted benzenes, that is, the substituents on the benzene ring are identical. One easy way to do that would be by establishing the number of different types of carbons and hydrogens which are in the ring, and that would equate to the number of different carbon and proton signals you would see in the carbon and proton NMR. So for this molecule, which is highly symmetrical, if you played the substitution game on it, you would see that you have only two types of carbon. We have the carbon attached to benzene, and then we have all of these other carbons are equivalent. And in terms of hydrogens, we only have one type of hydrogen in the molecule, so you would have two carbon signals in the carbon NMR and one proton signal in the proton NMR. Moving to the 1,3 or meta-disubstituted benzene, so this is the para-disubstituted, this is meta-disubstituted. In this case here, you have, this is definitely a unique carbon and hydrogen. This is as well, and this is as well. And then in terms of carbon, so they're in carbon, we have 1, 2, 3, 4 types of carbon, and we have 1, 2, 3 types of hydrogen. Lastly, orthodisubstituted benzenes, again highly symmetrical. In terms of numbers of different types of carbon, we have 1, 2, 3. There's a line I can draw right through this molecule, and one half reflects the other. So we have 1, 2, 3 types of carbon, and we have only 2 types of hydrogen. Therefore, simply by looking at the proton and carbon spectra and counting the signals, you could distinguish between ortho, meta, and para symmetrically disubstituted benzenes. Moving on to unsymmetrically disubstituted benzene isomers, three of which are shown here. You have para, meta, and orthodisubstituted benzenes. I just chose these two because I could find the NMR spectra for them, as you'll see in a moment. Let's take a look at the number of different types of carbons and hydrogens that are in these molecules, and we can establish the number of different carbon and proton signals that we'll see in the corresponding carbon and proton NMR. The simplest spectrum, that is the compound that would have the fewest number of peaks, would be the one that is the most symmetrical. And of the three, this is the most symmetrical. There is a line going right through the nitrogen, the carbon, this chlorine. One half of the molecule would reflect the other half, and therefore this would be the simplest looking one and the easiest one to pick out of the three. It would have two types of hydrogen and 1, 2, 3, 4 types of carbon. And the proton NMR spectrum looks like this. We have H1 type of hydrogen, and we have the second type of hydrogen labeled H2. Each one sees each other and splits each other into a doublet. So this is a typical pattern for a unsymmetrically para or 1,4 disubstituted benzene, and the chemical shifts happen to be a little bit far apart. Sometimes they're even closer together, which makes it almost look like a quartet. But these are definitely not related to each other. This is for one of them is for H1 and the other one is for H2. Let's move on to this example here. How many different types of peaks, or how many different types of hydrogen are present? How many different types of carbon are present? What would be the number of peaks in the proton NMR and the number of peaks in the carbon NMR? We have 1, 2, 3, 4. All of them are non-equivalent. If you did the substitution game on this, every hydrogen here is not equivalent. And in terms of the number of different types of carbon, well, again, this is not a very symmetrical molecule. So you would have 6 different types of carbon, and you would have 4 different types of hydrogen. So in the proton NMR, which is shown here, I see 4 different types, 4 peaks. This peak here, which I've highlighted and I drew a little line to, this is just the solvent in which the sample is dissolved. So if you ever see a peak at around 7.24 ppm in a proton NMR spectrum, that is just the solvent. It has nothing to do with the compound itself. These are real spectra, so these peaks show up. So now you can distinguish between meta and para disubstituted benzenes. What about this one here? How many peaks would you expect in the proton NMR? How many peaks in the carbon NMR? Again, not a symmetrical molecule, so you would expect to see 6 peaks in the carbon NMR, 4 peaks in the proton NMR. All right, now you have a way to distinguish between the para-unsymmetrically disubstituted benzene versus ortho and meta. How do you distinguish between ortho and meta, though? All right, what's the key difference here that you're looking for? And the thing that stands out is this particular hydrogen. Notice that it is on a carbon that is next to carbons which do not have any hydrogens. Therefore, it would resemble a singlet. This is the peak here. It's not completely a singlet because you have a little bit of long-range coupling with H2 and H4. However, of the 4 peaks, this is the one that resembles mostly a singlet. So therefore, this peak is this one over here. When you look up here, you do not have one of these landlocked hydrogens, a hydrogen that has adjacent carbons with no hydrogens. Every single hydrogen here has a neighbor to look at, and therefore it's a much more complex spectrum. So this is how you can discriminate between para, meta, and orthodisubstituted benzenes. The para disubstituted benzene will give you these 2 doublets downfield, again in the aromatic region, in the proton NMR. And for a meta unsymmetrically disubstituted benzene, it has a hydrogen which will resemble more like a singlet compared to the other peaks because of the fact that it has carbons next door which do not have any hydrogens, whereas ortho disubstituted benzenes, unsymmetrically disubstituted benzenes, have hydrogens on carbons next door, and they give a more complex looking spectrum. If you viewed the NMR review videos, you would have seen this already, but I want to point out, because it's rather important, that it is quite common for peaks to overlap in proton and carbon NMR. Even though you might expect to find, say, 5 peaks in the proton NMR, you may look and you may only see 4 or 3. And that is, it doesn't mean that the compound that you're examining doesn't have 5 different types of hydrogen. It just means that some of them might have, just by chance, they might be fortuitously chemical shift equivalent. It's perfectly possible for non-equivalent hydrogens just by chance to have the same chemical shift, and they sit right on top of each other. 2 examples involving aromatic rings are shown here. In the example on the left, you would be correct in assuming that you have 1, 2, 3 different types of hydrogen in this molecule, but when you look in the aromatic region, you only see 2 peaks. But we do have integration to help us out. This integrates to 2, this integrates to 1. We know there are 3 hydrogens. It turns out that 2 of these happen to be just sitting on top of each other. The other very important one I want to point out is when you have benzene as a substituent. That's called phenyl, right? A phenyl group. When there is a simple alkyl group attached to it, we do not have a strongly electron donating or strongly electron withdrawing group. It turns out that even though you have 1, 2, 3 types of hydrogen on a phenyl, they just happen to have the same chemical shift. They sit on top of each other in the proton NMR. So this is the aromatic region, and you have this large kind of broad looking peak which almost looks like a singlet, but it isn't. It's just a broad peak that combines the 3 peaks for the 3 different types of hydrogen here. If you see this, and integration will always be given or very frequently be given, if you see a peak in this region and it integrates to 5, it must be a phenyl substituent. Please remember that. So you might look at it and say, oh wait, I should expect to see 3 different peaks. If it integrates to 5 and it's in this region, the aromatic region, it has to be a phenyl group. Here is a practice problem in which you have to identify the chemical structure of this unknown aromatic compound given the proton NMR data, and you can see that there's an expansion in this region. The integration is shown over each set of peaks. We have an infrared spectrum in which 3000 and 1700 are marked off. We have a carbon NMR, and because of the fact that this is a real carbon NMR and it's difficult to get blow-ups here, I listed the chemical shift of each peak because some of them are close together. So this has 1, 2, 3, 4, 5, 6 different types of carbon. And no molecular formula is given, but a mass spectrum is given. And in the mass spectrum, you have the molecular ion, which tells you the molecular weight. See if you can come up with the structure for this, and a solution will be posted in a different video. And if we get a chance, hopefully we can do this together during an online meeting.